I'm really honored to address this group because you guys are incredibly special. And I actually like to think that you're going to lead the world in the next 20 and 30 years. So congratulations to all of you. Now I'm going to essentially describe, I was asked to describe a little bit about my own journey, and so I'm going to do that and try and give you a little bit of advice in a short period of time. And we'll see how that goes. But when I was asked to do this, I wasn't sure where to get started. So I decided to start with when my career really began, which was once I got my PhD. And you can see me here looking extraordinarily happy, getting hooded in 1993, receiving my PhD in chemical engineering, and getting my lab started a couple of years later in 1995, and establishing that lab. And this was sort of the beginning of my own independent research career. But a little bit of context around that, I got my PhD in chemical engineering in a program for polymer science and technology. And when I was a graduate student, I began building a base of mentors. And I had always been building this base of people who inspire me. I think this is something that we all do. And the reason I wanted to start with talking about this is because they have played such an incredible role in my life. And they still do, and this is one of the things I like to emphasize. These are just a few of the people who influenced me in different ways, and I'll just touch on a few of them to give examples of the kinds of people that you want to keep in your life or add to your life as you move forward. And I'll start with my own PhD research advisor, Professor Michael Rubner, who's now retired. He was a materials science professor at MIT. I was choosing my project and deciding which faculty member I wanted to join for a lab. And I found at least 3 or 4 projects that were incredibly exciting to me, including Michael's. But what really convinced me that he was the right advisor for me was that I found him talking about not only his science, but he talked about the importance of the rest of his life. When we would make appointments, would say, you know what, 4:30 is too late because I got to get on the expressway because I need to see my wife, you know, and I live far away enough that I'm not going to, jeopardize that. I remember once knocking on his door and hearing music coming out from under the door. It turns out that at that time on Thursdays he had flute lessons, at 2 o'clock in the afternoon. Music was a part of his life, and he wanted to keep it a part of his life. He was pre-tenure. He was on the tenure track when I joined his lab, and yet I'm thinking, here's somebody who's doing incredibly well. He's on tenure track, but he's not afraid to put boundaries on when he works and when he plays and the time that he spends building his own life. Because I knew at that time I wanted to be an academic and I wanted to be heavily engaged in a research career. I thought maybe I can learn how to do that if I can be mentored by him. And indeed, he has been an incredible force for me, and he's always been kind of a life check. And sometimes he'll even reach out and say, Paula, you look kind of crazy there. How's your life? On the other hand, we see Bob Cohen, who was another member of my thesis committee and a faculty member at MIT during the time that I became a junior faculty member. Now, Bob Cohen was essentially the enthusiastic rallier, both on my thesis committee. Oh my God, that's such a great idea, and boy, I can't believe this worked out. What a wonderful idea, example. He was the one who gave me those boost words, the superlatives. He may not have known he was doing that. He is a very passionate, enthusiastic person. But when he was excited about my science, he made it very clear he was excited about my science. And that was something that I needed. I was in a world where I was, one of very few African-American graduate students. I was a woman graduate student. I didn't look like everyone else who was trying to enter academia. Having somebody who really knew, as an established faculty member, what was good, tell me I was good, was important. Hearing it frequently was not bad either. And I think we all need somebody who's going to remind you that what you're doing is great. And Bob was that person. And a couple of side stories about Bob. I found out a few years later, when I was applying for faculty positions, I applied everywhere but MIT because I was at MIT. I was approached by my department head during the chemical engineering meeting, and he asked me, I hear you're applying to all these places but not to us. Why is that? And I said, well, I'm from MIT. He's like, let's talk. You should send in an application. I found out maybe 10 years later that it was Bob Cohen who told Bob Brown, the then department head, that I was doing this and that he really needed to make sure that I sent in an application to MIT. So Bob actually influenced where I ended up. But finally, as a junior faculty member, one of the things that was most important for me was, along with his constant mentoring, I was able to sit in a faculty meeting with Bob Cohen present. And as we were reaching the end of the faculty meeting, have Bob get up and say, well, I have to go because my son has a baseball game. And now this is in the mid to late 90s, and you're a junior faculty member, and I had a small child, but I felt like I had to sit constrained and not say anything. But having him get up and say, I have a priority, gotta go, made me feel comfortable claiming my own priorities and my own needs. And that was something he also did not realize he was modeling, not just for me, but for the rest of the faculty. Now, there are other examples here. I give Arnie Stansel and Jim Gates, who were exemplars of African Americans in my field of chemical engineering. Arnie Stansel headed up a huge part of ExxonMobil, and then in the latter part of his career became a professor at Georgia Tech. Jim Gates was a professor back when I was an undergrad. Then he went to Maryland and became kind of this incredible rock star of dark matter physics and so forth. But I just liked knowing that these people were out there. So there are different kinds of people that you need in your life. Some of them you don't even have to be in constant contact with. Finally, my peers in my life had a huge amount to do with where I am today. And I'm showing a few examples of women who became faculty members in or around the time that I did, and also had a number of things in common with me. Many of my peers, women, both women majority and women of color, a number of other peers, people you could exchange your difficulties with. You could actually say, does this seem normal to you? And I need to talk to you. I just got this review back, and it's horrible. You're able to actually sound each other out and then talk about how you're going to move forward. And being able to do that and to have other people inspire you who are your peers is incredible. So sort of the takeaways from that is that reaching out to others and embracing and incorporating them into your life provides you with a network that can be incredibly empowering for you. No one truly prospers in isolation. No one stands alone. And that is true for any research career, any scientific career. All aspects of life benefit from the input of others, and therefore, having a mentor who gives you or shines light on how you might handle other parts of your life, as well as your scientific career, can be incredibly helpful. They also play invisible roles in moving your career forward. There are people pushing for you, and you don't even know it. So, continue to have an open and embracing approach to the world, and you'll find that you'll begin to expand the numbers of people who are able to give you this kind of mentorship. Finally, it's important to find mentors who can give you a critique, sort of that critical perspective on your work. I had someone like that in my thesis committee, and then as I advanced into my faculty career, there were always people that I thought of as, skeptics, but, friendly skeptics. It's good to have those friendly skeptics around so that you can bounce ideas off of them and you can determine what the negative or aspects that you may not have considered are in your work. When I started my lab, I was engaged in a couple of different areas. One of them was the electrostatic assembly of polymer thin films. This is a slide that I often show, which shows this alternating electrostatic assembly method, which can also be one based on hydrogen bonds and other interactions. And in our lab, we were really focused on, initially, how we could control these electrostatic interactions on different surfaces and actually use micro-patterned surfaces to direct different electrostatic and colloidal systems in a way that gave you this very elegant control. So this is sort of what I was getting started with in my lab, and a lot of this was influenced by my postdoc, which was in the Whiteside's lab, in which I learned the microcontact printing method, and in my interest in self-assembly of polymer systems. And this was sort of the project that moved very rapidly because it was one that enabled rapid generation of data. But I also had a synthetic side to my work. My PhD was actually based on diacetylene-containing segmented polyurethanes and liquid crystalline polyesters. So, you know, I was really heavily involved in polymer synthesis and complex material systems. And when I started my lab, I also had a part of my lab that was focused on liquid crystalline block copolymers because I was really fascinated by this hierarchical order. I mentioned these early projects because they don't look anything like what I'm doing now. And it turns out that as you evolve in your career, you will begin to take the general principles that you've learned and apply them to different kinds of problems. And that's absolutely what happened in my own lab. But this was certainly where I began. One of the things that helped me advance my work and move forward was actually taking hold of an opportunity. And this is something that happens throughout your life, and it's important to recognize when there may be a life-changing or a significant life-enhancing opportunity that you face. When I was still a junior faculty member and working on these projects that I just described, I had been involved in a MURI, which is this multi-university engagement, and that had me working very closely with my colleague Tim Swager on my campus and with others. At some point, because we were in this MURI, we got an announcement about a UARC, a university-affiliated research center that was envisioned to use nanotechnology to provide a range of protective systems, material systems for the soldier, be it involved in armor or remediating health or sickness, this kind of thing. And I read the announcement and emailed Tim and said, you know, this sounds like something we could do. What do you think? And then he checked it out, and we started talking to each other. Then, Tim said, this sounds great, but we need to rope in Ned Thomas, who was at that time heading our polymer science program. And ultimately, we built a team at MIT. And I was a junior faculty member. I was probably 5 years in at the time. It was probably 2001, so 6 years in. So I ended up becoming something like the facilities manager, but nothing really key. But was heavily involved in sort of the structure of the institute. And this was something that had a huge influence on my own research career, but it also provided a resource for the rest of the campus. It involved ultimately 30 faculty at the time that we launched in varying degrees. It was a $50 million center over 5 years, and it's been renewed since then every 5 years, and is now in its 4th cycle. This is actually some of the paraphernalia, the things that came out when we first opened. And in my own lab, we began advancing. The liquid crystalline block copolymers became, high-strength polyurethane material systems for textiles. And that's where some of my students, like LaShonda Corley, began to develop and work in self-assembly. That later evolved into a range of different other systems. And because it was a very collaborative center, I actually used it as an opportunity to engage with a new faculty member, newly arrived from Texas, Austin, Angela Belcher. And so you have to get involved in this Institute for Soldier Nanotechnology. She did, and we ended up working together on something that in the end had nothing to do with soldiers at all, but because it provided an environment for us to collaborate, we ended up looking at how we could combine the thin film assembly that we did in our lab. And at that time, we were really focused on ion transport and conduction in these thin films. And her work with templating viruses. She was able to essentially design or essentially evolve these phage so that they could display proteins that promoted the capture and then transformation of metal ions to metals and metal oxides. So we began working together on essentially a virus-based thin film battery. And we did this work with another colleague, Yet-Min Chain, and this actually led to a huge amount of collaboration between me and Angie, which has now evolved into looking at how we can design materials to address ovarian cancer. So it led to these lifelong collaborations. This is a memorable picture from 2009 when Barack Obama was president and had black hair instead of gray hair, came to visit MIT to describe his energy policy for the first time. And a group of us were able to describe our energy-related technologies with him. And there's my colleague Angie and our student, joint student Becky Ladusky, Angie's student, and a couple of other faculty members who were involved in that visit. We also, as I began to evolve my work toward biomedical and biomaterials, which I'll describe in a little bit, we're able to use this platform in the ISN to understand more about the problems that face soldiers on the health side of things. And this is an example of some of the technologies we've developed in that area, including hemostats that are rapidly deployed to stop bleeding in soldiers. Now, a lot of this work was inspired by the kinds of problems that were presented to us through the perspective or the lens of the soldier in need. And that actually was a wonderful way of allowing us to innovate around important technologies that could have impact across the range of different applications, including civilian applications. So I mentioned that my research program changed a lot. And this is just a short summary in one page of some of the steps along the way and how it evolved. Essentially, I started with this sort of foundational viewpoint of how we can selectively deposit material systems on surfaces and how we can get hierarchical order in polymeric systems. And I began rapidly to look at electro-optical and electrochemical applications based on the same systems. But then I took a sabbatical in 2003 at Caltech. And I had a number of friends there. I was hosted by Dave Terrell and Julia Kornfield. And Julia at that time was working in an area very close to mine in liquid crystalline material systems. But Dave Terrell was essentially directing his work toward the use of cells to generate unique polymers, biopolymeric materials. And I ended up spending a lot of time in his lab, listening to lab meetings and subgroup meetings, and basically understanding a new language because I didn't know I only knew a little bit about biology, just sort of basic. At that time, we didn't have Google, so I couldn't Google all of the terms rapidly. But over time, I began to understand a little bit more about biological systems and how to manipulate their interactions with materials. And that was actually invaluable to me. I also spent some time talking with Mark Davis, who was a chemical engineer who had taken his work in sort of the nanomaterials world in catalysis and moved it toward addressing cancer because of his own personal experience with his wife and cancer. So he had a lot of experience in writing NIH grants. I got to sort of see what an NIH grant should look like. It's very different from an NSF grant or a DoD one. So I got a lot of input during that sabbatical and also was able to readjust and realign my work. So it is important not only to seize unique opportunities, but sometimes if you can't arrange an official sabbatical, if you can arrange a time away or an immersion in an area that you think is going to be important or interesting to you, it can have a very meaningful effect. And I don't think this would have happened if I hadn't planned it. I think that if I had just sort of, skipped past the sabbatical or done something much more routine, I would not be doing what I'm doing now. It required being in a different environment and being inspired by others. Now, after that, I began to investigate biomaterials applications with the systems in my work. And this picture is actually representative of this sort of transformation because these are two students, Dan Schmidt, who was in sort of the electrochemical side of my lab, and Chris Wood, who was this really eager student. He was originally a summer intern in my lab and then came back so eager to do drug delivery. And this is just when these ideas were germinating. I had just started a collaboration with David Len, who was a postdoc in the Langer lab, because I gave a talk in the Langer lab about patterning of thin films. David came to me later and said, you know, I have these degradable polyelectrolytes, maybe that can help you pattern. And I thought, I don't care about that. Let's see if we can make a drug delivery system out of that. So we began working on that. Chris Witt was the undergrad who was helping us. And then when he came back as a full-time student at MIT, he convinced me to join his lab. I had no funding. So I actually had to use my discretionary money to fund him. And he created this joint project. We made Bob Langer a co-advisor, so I was able to kind of go back and forth between the labs and do this work because I had no biosafety cabinet. I had no, no way of doing cell culture. So everything was done sort of on the lam, and it's because of him that we were able to actually advance. And here we're showing kind of a combination of these two students where Chris and Dan worked together on an electrochemically active drug delivery system. So our lab began to combine the technologies, and that was actually very rewarding from my perspective. So along this timeline, you see that I got excited about this in 2003, and the first grants came between 2006 and 2007. There's kind of like a 4-year period where I'm sort of leveraging all of this stuff through the goodwill of my colleagues and students who were excited, but I had no money for it. And that was actually a rough time. There's this feeling of investing in something and going in the red and not knowing if this is going to work out. There's also an experience of feeling that on some level, some part of the world was pushing back on me. And I felt that only in small bits and pieces before, but I felt it more at this time. Maybe because there was a perspective from some in the community that here's somebody I've never heard of. They're not sort of from a bio group, but they're trying to do bio work. Maybe it was simply a bit of overall skepticism, or the fact that I was still learning how to articulate our problem set and how we could use these systems to address it. But all of those things were kind of discouraging, and I had to use a network of friends and colleagues, not only to look over my grants, but to remind me that this was possible. So my message to you is to hang on and to continue to feed your vision, even when there is a bit of disagreement about it. It's good to hear from others what the possible problems are with what you're proposing. But if you have a well-grounded concept and you truly believe in it, you have a vision, then continue to work on it, continue to shape it, and find ways to feed it and even expand it, regardless of what you hear. You let negative experiences inform you without degrading your will. For example, the kinds of reviews that you might get when you submit proposals, or the lack of response that you may get initially when you try to make a shift in your work. One of the things that I always told myself was that the reason that I'm staying here and I'm working on this problem, even though this is a crowded field and there are a lot of people working on these kinds of problems, is that I believe I have a unique perspective. I have a different skill set, I've had a different journey, and so I have new things to bring to this. And in that way, I was able to sort of reaffirm that this is something that we really want to do. I think this is something you have to sort of tell yourself multiple times. Don't be afraid to think big. Be able to articulate your vision in a way that other people get excited about it so that you can begin to get some momentum in getting your first ideas out there. And definitely don't be afraid to expand your expertise or dive into a new thing, even later in your career. A lot of people will say, well, you're so well established in A, why are you going to venture into B? And I would say that's definitely not something that you should listen to. Always go where your interests and where your heart pull you. And always keep looking for where the next new step might be. So my own vision with the electrostatic assembly was that we would be able to replace a more traditional polymer coating that is going to have some limitation in how much drug it can contain because of polymer thermodynamics. so you'll have low loadings, usually requires solvent and heat, and therefore is not great for biologic drug delivery. It also doesn't give you control over rates of release. And in this case, the idea was that you could build up films layer by layer and then release these drugs at different rates and different times, and that this would give you not only much greater loadings, because thermodynamics are now on your side and you can load up a lot in this electrostatic assembly approach, but you can incorporate biologic drugs like proteins and siRNA, nucleic acids, and this can be combined with the incorporation of small molecules so that you get these very highly tailored thin films. And the work that we've done has led us to look at everything from sort of spatial temporal control of bone and tissue regeneration and wound healing, siRNA release, to control and address wound healing, and targeted nanoparticles for cancer delivery. So this gets to the Koch Institute. So this is a second, the Institute of Soldier Nanotechnologies was something I was directly involved in and founding, and it really shaped where we went. But the Koch Institute had a huge impact in how well we could integrate our materials, chemistry and science, into real-world problems. And the reason for that was that it brought us together with biologists and clinicians. The vision of the Koch Institute was to put us all in one building, and essentially there were already 13 cancer biologists who made the Center for Cancer Research, this famous center with Nobel Prize winners. The Koch Institute idea was to combine that with a similar number of engineers. So we ended up with 13 engineers, and we all moved into this building together in 2010. Now, it's worth mentioning that Tyler Jacks, the director, was very careful in making sure that the engineers talked to the biologists. In fact, he did this kind of Noah's Ark thing, where there's like 2 engineers per floor, and the rest would be biologists, with the exception of the top floor, which was sort of Bob Langer, but he needs some space, and a highly integrated group there. But it made us sort of get into the elevators, and we have essentially a coffee shop and food on the first floor. It made us interact with each other, and these multiple body collisions led to a huge expansion in collaborations. From my own interactions, there may have been 3 or 4 in the first year, but from my students' interactions, this was multiplied, so that there were maybe something like 10 or 12 new collaborations and interactions within that first 1 to 2 years that we got started in the Koch Institute. It also led us to look at much more realistic animal models for our work. It led us to work with people who understood biology. So here we have Mike Yaffe, who's a systems biologist. He was able to essentially give us a much better idea of how timing of the release of a drug and order and sequence may also have an influence on a treatment. It also created a community. This is an example of a nanoparticle flash dance that we had with the Cambridge Science Festival, in which this is a cancer cell, and somewhere way in the corner, it's hard to see, there's a group in yellow, that they're the nanoparticle attacking it. We do all kinds of things together, and that really builds community. And this gets to my last point, which is that one of the things that you will do as you move forward, you already are leaders, you will begin to direct labs or groups, whether you're in industry, starting a company, or you're a faculty member, and you will be the person who creates the environment that these people work in. I found it to be incredibly important to intentionally build a positive and affirming science culture. And I say intentionally because we all think that is what we're doing. I mean, we all believe that we're creating a good environment, but it actually takes a consciousness to be aware of what's going on with your research group, and understand when there are dynamics that may be keeping some people from participating as fully as they would like and as you would like. So being aware, being very careful about who you let into this group, but also being aware of how those interactions are going, moving along, and making corrections. There's You know, this sort of idea of the bystander playing a role when there are issues of harassment or bullying. I would say that as somebody who becomes a leader in a group, you are forever in this role of speaking up and making those corrections. If you don't, you won't hear from everyone in your lab. You won't be able to get all of those different perspectives and voices that you want to have. The diversity of those voices is important to be able to get the innovation out of your science. Problem solving is much more effective when everyone's voice is heard. And also, you get new problems and new perspectives that are brought in if you can get those voices out. So this is snapshot of my lab, and also one of our attempts to, this is a Halloween costume where this is a self-assembled polyelectrolyte complex, where red and blue are plus and minus, and I'm a substrate of some kind. You know, having fun with your group, with your team, is an important part of building that experience. Finally, the people are really what make the job special. There are a number of people who have been in and out of my lab, but remain in my life, and I continue to mentor, and I'm proud of every one of them, the ones who go off into industry and become excellent leaders, the ones who are leaders in academia. And one of the things I'm especially proud of is the diversity of faces that I have, and the number of different countries and the number of different backgrounds, because I feel like I've learned something from every single one of those experiences. Finally, select your lab, your science, and your life partnerships with care. The whole idea is that you can actually take the time to build meaningful relationships and nurture them, take care of them, reach out to people, be there for them, and they will be there for you. And make sure that you find the unique fit that works in these collaborations, in these teams. Engage people that you love to spend time with, because you're going to spend a lot of time in any huge or enormous research effort. And while you're doing that, build a complete life. Remember that you are an entire person, and that you need to feed every aspect of your life. You are the only one who gets to determine how that balances out. And the balance will look different at different times in your life. But family really matters. And these are sort of images of my family in different points. Vacation matters, because you do need to take a break. And the people that you spend a lot of time with, they matter too, and you want to cultivate that. And this is just a few of the images of people I spend time with. I like this one in the corner with me and Angie Belcher and Sangeeta Bhatia, pointing out that we look like engineers on our signboards. Mike Yaffe calls me his little sister of science. Another few images of my lab. They let me get in front in this picture with the boats, because I was way, way behind in the boating. And create camaraderie wherever you are. Make sure that you keep that spirit going. And in the process, generate your own moral support system of people who will help you out. And here are a few images of people I've collaborated with who are great friends of mine and have made my research journey an incredible one. So I'll stop there, and thank you for the chance to talk with you.